All right, Priya, I think we'll get started. If you can move to the next slide, please. Good morning, everybody. My name is Heather Galt. I'm the Vice President of Marketing here at PPO, and I'm really excited to have all of you with us this morning. We're going to jump into the science of spectroscopy, and a couple of folks from our team are going to be sharing a whole bunch of information with you, so I hope you have your brains ready. Let's jump into the agenda, Priya, if you don't mind. And we'll take a look at what we're going to cover this morning. So we'll start off, Priya, and who I'll introduce in a minute, is going to go through the science of spectroscopy. So introducing us to the concept and some of its history, talking through some of the components, so imaging systems, prisms and gratings. We'll go actually inside the spectrometer and take a look at the components. And we will talk about the spectrometer system itself. At the end of that, we're going to take a little virtual tour. So we're going to have an opportunity to see inside PPO's labs and some of the work that goes into getting our spectrometers and our lights ready to be installed in a food plant. After that, Michael will take a little bit of time to go through the applications that we consider for food processing and look at how we can automate inside a food processing plant using our system. A couple of housekeeping items before we get started. So first of all, if you have a question at any time during the presentation, please use the Q&A function, which is down at the bottom of your screen. If you move your mouse down to the bottom, you'll see Q&A. You can click on that button, ask a question, and that will come through to us and we'll be able to answer it for you. If you want to chat with everybody who's on our webinar today, so you can use the chat function, but please be aware that that chat function does show up publicly, so everybody on the webinar will have an opportunity to see anything that goes into that chat. We are recording the session today. That should be showing up on your screen as well, and we will be posting that webinar along with all the other webinars we've run so far on our website at ppo.ca/resources. So please feel free to take a look. We'd love it if you watch them again. If you haven't seen them already, please feel free. And we'd love it if you shared them with your colleagues as well. I hope you find them helpful. So without any further ado, I'd like to introduce our two speakers for today. First of all, we have Priya, and Priya Krishnaswamy is our optics designer here at PPO. Priya has about 15 years of experience in designing and building optical systems in a variety of industries like automotive, aerospace, handheld electronics, robotics, and food processing. Priya has both a Bachelor of Science and a Master's of Science in Physics. We also introduced Michael. Michael Griffiths is an application specialist here at PPO. Michael's worked in process management and QA in food processing industry, first at Maple Leaf Foods and then at Canadian Mist Distillers. Michael's been an application specialist with PPO for the last 3 years, and he comes to us with a Bachelor of Engineering and a Master's of Engineering Science in Biomedical Engineering. So they're both very well qualified to be presenting to us today. So Priya, I'm going to turn it over to you and let you get us started.
Thanks, Heather. Hi, everyone. Welcome to today's webinar about the science of spectroscopy. In the last two webinars, we talked about a new approach to food inspection. We touched upon topics that included hyperspectral and multispectral imaging, vision systems, and we also talked about data and AI. So today we are going to learn about the underlying science on which the system is built and how automation comes in, bridging the system together with AI. So let's start with the introduction to spectroscopy. The two images you see here needs no introduction. It questions the limitations that we have, and at the same time, it is also having question on what is a limitation on manned and unmanned missions. And yet in 1800s, we were able to figure out what the solar spectrum was made of and what its atmosphere consisted of. Today, we are looking up into the space, trying to find planets that's outside of our solar system, whether they have water in it. So how is that possible when something is so far off, and yet we have information powerful enough to deduce its chemistry? It is through the science of spectroscopy. And what you have here is a solar spectrum, and we are used to seeing the red, blue, green spectrum. And you have to understand that there is also infrared and ultraviolet region. And we'll focus today on this visible region. And there's enough information within the spectrum to tell us what are the elements that's included in the solar spectrum's atmosphere, sun's atmosphere. So let's look at what helps us deduce this information, that is the fundamentals of spectroscopy. And here you have a halogen beam, and as I had mentioned, you have the blue to red region of the spectrum, and beyond you have the infrared region and the ultraviolet rays. And here is an element where you can see there is suddenly some dark lines, and these dark bands indicate that there is some absorption happening at those specific wavelengths. And if you take that element and bombard it with enough energy or enough electrons, they would emit light just in those specific bands. And the fun part here is, the beauty of this is, every element has its own signature. And once we understand what the absorption and emission spectrum is, we can go back and deduce its chemistry. So just like what we saw in the solar spectrum, there are actually dark bands here. And once we could understand what these dark bands are and what the pattern is, it was easy to figure out what elements were present. And these are called Fraunhofer lines. So this comes back to the next question. Now that we know the underlying science, how do we gather this light and how do we extract this powerful information? We are going to go into imaging systems to understand that. So now that with the advent of, now that everyone has a smartphone, everyone has a camera in it, and we're always taking images. And most of the time the question is, how big can I make the image to be? Can I frame it? Is it going to be 4:6 or 5:10? And once I start enlarging it, I'm starting to see a lot of information that's missing. So it's not crisp. And we always say there's not enough resolution. So what do we mean by when there is not enough resolution? Basically, the colors are fading in between two regions, and there's not enough information that I'm able to pull out. So how about a moving object? Because we are in an automation system, an object is always moving. And there's a still object, and I'm taking a picture of it moving. And again, there is a lot of information which is missing. So how about the lighting conditions? Again, I have an image with lighting and one with minimal lights. And you can right away see that the one on the left has information on the colors, the one on the right doesn't have enough information. So how do we solve these problems? So these are problems that's always going to be in an imaging system. And we have to understand that an imaging system includes having a detector, an optics, lighting, and that all of them get together to form the final solution. So how do we gather light from here? That is, which has enough information. So we all know about optics. What optics does is it gathers enough light and it gets imaged onto a camera. And for example, when I take an object, these are like 4 dots. And once we image, our expectation is that it's going to image in the same fashion, having 4 dots, perfect. However, there's a whole lot of aberrations that goes into optics. And these are aberrations which if not taken seriously, is not going to help us get a well-resolved image. So the question is, can this be corrected, right? This is a picture of people at PPO. And I would say a picture is always worth 1,000 words. So this is a simulation that I have run through ZMAX. And you can see that the first one is that of a single lens, and the second picture was taken with multiple lenses stacked together. And since there are many problems, there are many types of aberrations, one single lens is not going to help solve it. So we always add more optics to help see the entire field of view very clearly. So PPO optics are designed and built inside so that it suits the application and the resolution that's required. So now that we have solved the problem of optics, do we have a camera that is good enough to get all the signal properly? For this, the best way is to imagine ourselves sitting in a room right here. You're able to hear me really well, and we don't have to bother much about noise. But let's accept this is not going to be how the real life works, right? So we can be outside where the noise is now kind of creeping up, or we could be in a rock concert where we'll always have to shout to the other person to get some to be heard. So where do we want to be? We cannot keep on screaming at the other person. We want to be somewhere at the first place, and which would mean the noise, there's going to be some noise level, but it can be calibrated out so that we have enough signal to make sense of sense of the object that we are looking at. So the question is, how do we get yourself heard? Higher signal to noise ratio. And now that we have looked at noise, we talked about optics, and we talked about resolution. So when we generate an image, for example, we have the PPO logo here, and there's always going to be one object and many possible images, because optics, camera sensor, and image processing, they're all working in together. So if we have a problem with one of them, we are going to have this issue coming up. So noise is unavoidable. The reason you can see in the last image here, the logo is clear, but there is a lot of noise. And we have to understand that I have said yes to this image because noise at large is unavoidable. The question is, can it be calibrated out? However, in the first image, there is nothing. If I'm going to take any information, it's most probably not going to be relevant. I'm not going to get the color right or the structure right. So it's very important that the optics, camera sensor, and image processing, they all work in tandem to get the best possible outcome. Now that we have that image, now we have to go to the next question. How do we extract the spectral data? To that, we are going to go through prisms and gratings. So this is a picture which easily pops up in our mind when we talk about a prism. We know Pink Floyd made it popular. You have white light, and this prism splits the color white light into its multiple colors. And it was very important because it helped us understand that white light in itself is made of many colors and its constituents. So we use gratings, and in gratings, it works on the principle of diffraction. So it has, as you can see, it will have multiple lines, and we are talking in terms of 300 to 1,000 lines per millimeter. And light goes in and it splits up into many bands of the rainbow that you are seeing here. So a grating, why use a grating instead of a prism? Because it provides increased spectral resolution, and it also provides better signal. And we all might be thinking, it's a complete new concept and there is no way I'm going to understand it. And this is an animation showing how a grating is formed, because you have plane waves coming in, and you could have seen it in how water comes through rocks and they form waves, and here you can see it is destructively interfering, and the other one is like the peaks coincide and it constructively engages. So you have the bright and dark lines, and gratings are built through interference patterns. So this is how a gel grating looks like. And we might be thinking how, grating is a completely new concept. However, we come across gratings in our day-to-day life. So the one popular example we can look at is a DVD, where it has multiple lines and you have light falling on it, and it shows this wonderful rainbow effect. It's because of the principle of grating. And some of the deli meat you would have come across in your day-to-day life would have this rainbow colors. It's nothing to do with the meat. It's just that it is cut against the grain, and you have all the fibers showing up, and it acts as a grating, and you see this effect. So we manufacture gratings at PPO, and here is Romek, and he's the founder, and he has a patented method of gel-based grating. And it's important to understand how the gratings are made well, because we talked about noise before, and you can see here as an example between a competitor and P&P Optica's grating built. And our gratings have no ghosting. The signal is very clear, the noise is low, So there's less noise to factor in once you start building up the system. And it's very important because more signal to noise ratio, the better your the better your identification is going to be. So let's build a spectrometer now. So this could be a familiar picture in your head when you talk about meat with foreign objects and some without foreign objects, like running through the belt. And the question is, if I'm going to take the entire picture and have spectral data on it, if the end signal would have too much information for us to gather. So how do we scan this line in itself? It's the usual way we would to scan a document that is going line by line. So you just mask a portion of it, you run through the first line, you go through the second line, and you keep looking at it. And by the end, as the belt is moving, you would have the entire information with you. But we cannot do it on the belt. So what we do on the spectrometer is we add a slit. So now that we have talked about the building blocks of spectrometer, how does a spectrometer look? Here is a snapshot on, this is a cross section of how a spectrometer would look. And you can see that there is a lens, you have a slit, and you have a couple of lenses, and the grating sits in between, and there is a detector. And if you want to look at how light would go through it, we have the next slide to show that. So you see that the light goes through the first, this is the slit, we are starting with the slit, and light goes through the lenses. And at the end of this last lens, you can see that it is almost parallel. We call it, it is collimated, and it goes through the grating where light splits into multiple colors. And you can see that there are close to 5 colors, and every color represents different wavelengths. And you can see that all the pink comes to one focal position. So that is all of one wavelength comes to a focus, and now you have all the wavelengths in focus, and you have enough information from one point to all its constituent wavelengths. So when we scan an object, you need a reference light. So let's have a halogen light, which has all the colors continuously. And once you start scanning it, you would see that here is a foreign object, and it has specific bands. And here we are looking at meat, and it has some bands, absorption bands too, except that the two absorption bands are completely different. And we talked about the importance of absorption emission being very specific to materials. And this would help us understand that there is a foreign object at a specific pixel, and that there is meat at another pixel. And the question is, like, are there corrections applied to it? Yes. What you see here is what we call a SMILE. So when once the spectrometer is built together and you have an argon lamp which has discrete wavelengths, and you would expect them all, and the different line bands you're seeing here correspond to different wavelengths. So this is one wavelength, and this is around 965 nanometers. So you would expect it to be a straight line, but because of aberrations in optics, you have the curved lines. So we run a calibration through it, and after correction, you would have it all straightened up. What you would notice here is in spectral line, you are seeing 0 to 500. They are the pixels of the camera. So once we run a calibration, you would now have all the pixels mapped to wavelengths here. There's one more correction that is added. For example, we take a white target with black lines. You can imagine to that of a barcode reader here. When we are planning to, when we image the system onto a spectrometer, these are the expected lines. So basically, there's no light coming, there's not much light emitted out because it is black. You would expect the straight lines coming along and on the spectral side. Instead, we get straight lines, and if you look closely, they are slanted at the edges. This is what we call as keystone. And after corrections, we see to it that, and after corrections are applied, the lines are straightened, and it's corrected here. So how do we illuminate the object? So now we spoke about how a spectrometer is built, how the resolutions come into place, how the corrections are done. But the next question is, we need to have a reference spectrum to analyze. So that's where the lights come in. So these are the lights to help illuminate the product. And there are two types of reflections that we come across in our day-to-day life. So one is specular, similar to that of a mirror, where it reflects back properly and it is crystal clear as an image. The other is diffuse reflections, where, as you can see here, I can make out that there is a tree, but the image is not very clear. So in this diagram, you would see that the reflection is having a bigger angle, and this is important because in our application, because it's not just surface level that we are looking at, but there is some underlying light distribution that has to happen for example, in case of meat, and which helps us understand the chemistry better. So the lights at P&P Optica that we have built here are diffuse reflectors. And to the right side, you see a built and assembled lights with reflector. So now that we went through the system and how a spectrometer is assembled and what makes a spectrometer, here's an image of me running through a belt, and we discussed it is spatial side, which is the width of the belt. Then you have the belt motion, and the z-axis is going to be the spectral direction. And once everything is done, you have a complete smart imaging system where the spectrometer is built, calibrated, and the entire system is designed and calibrated in-house at PPO. So once it's done, we are going to look at a final run and a measurement. So you can see onto the left of the screen is our original image, and onto the right there's a corrected image. And the next question is, how do we see the spectral information, right? Now, all you need to do is slice through the image, and you would see the rainbow of colors. And with that, we would know, we would be able to analyze the chemistry of foreign objects and the chemistry of the meat that we are running through the system. The next, we are going to have a video about how we characterize, about a lab tour at PPO, how we characterize our system, how we calibrate it. It's important to calibrate each and every system to the same spec, because it's easy to swap out our system on the field, and it's easy to calibrate because every system that we are building can be taken back to the same specifications.
Hi, I'm Alan. I'm a software developer here at PPO, specializing in industrial cameras, frame grabbers, and the camera interface to our software and in the system. The cameras, when we get them, they're pretty expensive near-infrared cameras, and they're idiosyncratic, so they need some testing and checking when they first arrive. And I do some sanity checks on them before passing them over to the optics group to make sure that they're ready to run our protocols and work in our machines with all their functionality. Some of the tests that I run here are looking for bad pixels on the camera. When we first onboard a new camera, we have to make sure that the performance is what we require. Make sure that the camera is running the same protocol and is going to work with our software. These are complicated software animals themselves, so we have to make sure that the firmware interface to the camera remains compatible with our software and will work in the system.
So now we had Alan talking about initial tests on the camera. We are going to go to the next slide, which is assembling the spectrometer. Again, when we assemble the spectrometer, we take care of a spectral range, and we look at spectral resolution so that every system is similar to the one built before. And that ensures that all systems are built to the same spec.
Now that we have characterized the camera, let's build a spectrometer. You can see that the spectrometer has been assembled here and connected to a computer. The spectrometer includes a slit followed by a lens tube, a grating, a second lens tube, and then the camera that we looked at earlier. The lens tubes can be moved within a reasonable amount to adjust for focus and field of view. The first step is to fix the spectral range of the spectrometer. I'm going to use an argon lamp because it emits discrete spectral lines. As I adjust the lenses, you can see that the lines coming into focus. You can also see the characteristic smile that we had discussed. I will now align the peak at 965 nanometer to a specific pixel position. This will be consistent across all spectrometer builds, making every PPO spectrometer build identical. Now that the spectral calibration is complete, we are going to adjust the spectrometer for its field of view. Now you can see there is an external lens to the spectrometer and it is placed at a distance from a target to mimic the PPO smart imaging system. The dark lines indicate the range within which I want the spectrometer to work, and with the halogen lights on, I'm going to again move the lenses. By doing this, I'm changing its magnification. I can see that the spectrometer is within the acceptable field of view and also in focus, so I will be locking this position down. The next step is applying corrections. We are going to start by looking at the smile. You will notice that the smile in itself is not symmetrical. We can fix it by gently rotating the slit around. After some patient work, the smile is now corrected. Now we will measure for keystone correction, which we had also discussed in the webinar. And here is the target. I'm going to take an image of the straight lines and apply a correction to it. Now that these tests are done, I'll do a final series of checks to make sure the spectrometer meets all the required parameters. And when I'm done, the spectrometer is now ready to be installed onto the PPO system. So let's go and see that.
So now that we have learned about building a spectrometer, we are looking at how it's installed onto a bigger system. The next video will run through that.
Hi, we just saw how a spectrometer is put together, how it is aligned. Now that it is aligned, we are going to put it on a frame. Here you can see the spectrometer, and you can see one more camera out here. This camera is going to see exactly the way our eyes can see, so the visible region, and the spectrometer here is going to see the infrared region. So the next question is, how are they both seeing the same scan line? So we have two mirrors here which are specifically coated such that this visible camera receives visible signal, and the spectrometer receives the infrared region of the signal. So the next step is to ensure that the camera, the visible camera and the spectrometer are looking at the same object, that is the same scan line. So to start that, here is the target with dotted lines, and it is set up on the table such that it is going to be parallel to the belt. And then I'm going to move the visible camera first and ensure that I'm seeing all the lines in its field of view. So to do that, I'm going to turn the lights on. Here I am adjusting the visible camera, and I'm moving it enough so that I'm able to see all the lines. I'm going to tighten it up here. And once this is tightened up, I'm going to move on to the spectrometer. And the spectrometer has some adjustment rings here. So I'm going to move that around until I see the dotted lines. So now that I have ensured that both the spectrometer and the visible camera are seeing the same scan line, which would mean they are going to see the object at the same time, the next step is going to be putting on the the calibrated lamps. So Danielle is going to show us how the lamps are put together and how it's going to come back here and how we run our calibration.
To begin with, I'll start talking about the various sort of styles of imaging system that you would see in the food industry. There are three main types, these being traditional vision systems, which utilize, I'll get to that in a second, multispectral imaging, and finally hyperspectral imaging. Now, these three technologies differ in terms of the type of data they gather and subsequently what functions this data serves. So for all these, I'll go back to using the same example that Priya had of the foreign material detection on chicken. In this case, there's various plastics as well as cardboard. So for a traditional camera-based vision system, it uses camera technology just like you'd see in your phone, where it's just looking at broad classifications of red, blue, and green for the wavelengths being analyzed. Now, this level of detail what you can determine is based on the relative proportions of these three groupings. So as a result, you'd be able to see very large differences like the bright blue plastic on the pink chicken. However, the white and clear plastics as well as the cardboard, as it's a more subtle difference in terms of the visible color, you wouldn't necessarily be able to pick up on this level of detail. It should be noted though that one advantage of these systems is that they do tend to be very high resolution. Just like with consumer cameras, for a very low cost, you can get a very high quality, high resolution image. Now, moving on to multispectral imaging. These systems utilize a lot of the same construction and principles that Priya had discussed. However, instead of looking at the complete spectra, these systems are sort of tailored design based on laboratory experiments to find out specific wavelengths of interest. So instead of looking at the hundreds of colors within those wavelengths, you are looking at a dozen or so. Now, where this begins to have a downfall is if you begin to see the introduction of materials outside of what was used in that initial system characterization. So with the case of foreign material detection, if you had an object coming from a different source that wasn't considered before, it might not necessarily be picked up. Additionally, if you were to change the product being run on the line, performance could also degrade. So this is where hyperspectral imaging begins to excel, in that you're filling in all these missing gaps of information and producing the continuous spectra for what is being seen, in a way seeing the chemical signature to its full extent. So looking at in terms of what this would be viewed like, here we can see in green the spectra of one of the plastic objects and the orange line representing chicken. There are very large differences between the spectra, which is immediately obvious at first glance. However, between the blue line and the orange line, both being chicken, it shows that based on the pixel by pixel classification, you can begin to see more subtle differences in what is going on. So you can get away from just, is this plastic or is this meat, and get into more the composition of the meat, or how does this meat different from like the pieces produced an hour before or yesterday or what have you. So here we break down the general outline in terms of where these three vision systems sort of excel and sort of contrasting traits. If you'd like more information on this, I would recommend seeing our previous webinar back in April on inspection modalities, as it went into more detail about these three vision systems as well as other inspection technologies. Now, getting back to hyperspectral imaging, there are some interesting features that can occur and be exploited. So here we can see a system verification target where it's bits of cardboard mounted within a plastic medium. So it can be repeatedly imaged to determine the repeatability of system performance. Now, one thing that's interesting to note about the plastic matrix for this target is that it's actually transparent within the NIR region that we are scanning. So while in the, it should be noted though that not all plastics exhibit this trait. This is a very specific trait for materials. So you don't have to worry that all plastics can't be seen. So for this specific material, as you can see in the visible spectra, it looks largely opaque on the black background. However, once imaging it with a hyperspectral image, it begins to look very see-through, and it's immediately obvious where you can make out the detail in terms of the features of the belt and behind. So this just goes to show that while some materials are look different within the various spectra outside of what we see with our eyes. And this is further illustrated when pulling up the spectral image, or spectral plot, sorry, for both the belt background in orange as well as the plastic target material in blue. You can begin to see very similar topographical features, just illustrating how little it is impacting the signal that we are seeing. Now, there is one downfall in terms of hyperspectral system. As Priya alluded to, there is the spatial dimension that the sensor is looking at. And in terms of the system constructions for the hyperspectral images you've seen, these have been at about a little over a millimeter in terms of the physical dimension that each pixel on the sensor is seeing. Now, in a perfect world, each sensor on a pixel of the sensor would be seeing one material and one material only. So in the case of foreign material detection, it is the sensor sees meat everywhere other than where there's an object, and then that pixel only sees meat, the plastic, thereby getting a perfect spectra for both materials, very easy to contrast the difference. However, in reality, this isn't necessarily the case. Objects can fall across multiple sensor locations, and each pixel might be seeing multiple materials. And as a result, wouldn't necessarily see a clean signal of chicken or plastic only, and instead see a combination thereof. This also goes to show that the minimum detection size doesn't necessarily relate to the overall resolution of the sensor. But with additional processing, you can begin to see more what is going on in the physical world in terms of what the system is actually seeing, and try to help overcome these issues, just seeing as not everything will work out like the perfect assumed situation. So along with this, how you present the product becomes a very important consideration for hyperspectral imaging, as well as vision systems in general. So hyperspectral imaging, as we are going off of reflectance, it is largely based on just looking at the surface. Now, there are some energies absorbed by molecules at the surface, as well as a bit of penetration beyond just the superficial layer. However, it's a lot lower energy wavelengths compared to that used in X-ray, where you are getting that full penetration through the entire thickness of the product. So as we are looking at these reflected energies largely from the surface, that is all we have to go off of when making a determination for foreign object rejection, composition, any of the such. So how can we serve to optimize products for this technology? So in the case of product geometry, we'll be looking at the situation of composition analysis. Let's say you're starting out with a trim-based product, so you have a lot of large, randomly sized pieces of meat. Overall, you would have a very low surface area to volume ratio, and due to this thickness, there would be some uncertainty in the measurements made at the surface, as throughout the thickness of the product, it might not necessarily look the same. So if you were to break down the product further in terms of grinding it for processing, you would be assuming that everything would look the exact same, only the pieces would be smaller. However, that might not actually be the case, and as you break down the product, you are exposing new surface areas, which will thereby increase the surface area to volume ratio. With this, you're getting an increased understanding of the true composition, as you're having to make less guesswork in terms of the thickness, for the thickness of the product. Additionally, this also serves the benefit of having a more uniform product size, especially in terms of imaging height, which is very important in terms of the system, optimal system performance. So here we are looking at some images of chicken breasts on conveyor, just to illustrate the different flow types. While I do understand that in terms of line setup, spacing consideration, technology available, that there's a multitude of factors that go into deciding how to set up a line. We'll just be looking at this only from the standpoint of optics. So one of the big issues with continuous flow and having large amounts of product on the belt is ensuring that the product is evenly spaced out and that you do not have overlapping pieces. This presentation of the product then ensures that there's as little surfaces hiding as possible. So for composition analysis, you're having to make less guesswork because you're imaging as much surface area as possible. And for foreign object detection, there is less hiding spots for objects to get by, as you are only looking at the surface and not necessarily looking through the product. Now, the one big thing is that the stacking of pieces can serve to degrade the optical system performance. This has to do with the system being set up to operate at a very specific imaging height for the focus. And just like with taking pictures with the camera, as you move out of that focal range, you begin to see blurring of the image, thereby losing the detail. So by having a uniform product height, you help ensure the integrity of the data that you're seeing. Now, you do get away with some of these height issues by having single pieces. However, the one issue that becomes more apparent is the edge effects, where spectral blending comes into play around the entire perimeter of every single piece. And this is a point where just seeing more and more product for the learning of the machine AI algorithms and machine learning comes into play in order to help truly understand what things will look like in the physical world. Now, the one issue that is needs to be considered for both types of product flow is shadows. So just like in visible world where you have an object and you see a shadow behind it, that's from the blocking of light, the same thing happens within the infrared regions. So on the right, in the hyperspectral image, you can see the dark shadows on either side of the chicken breast. This is due to having the two sets of lights, one upstream and one downstream. Now, where this begins to become an issue is in terms of classification of the material, specifically for foreign material rejection. It's with these shadows, you can begin to see the belt in the dark shadow areas look different than the surrounding background. And it's these misclassifications which could result in false positive readings. So factors such as lighting need to be taken into consideration when designing the experiments for developing models, as stuff like shadows, it happens in the physical world all around us, and as long as you have a light source in an object, it's going to be unavoidable. So overall, hyperspectral imaging, it serves to produce a very detailed image, specifically in terms of the spectral component. Now, do realize that there are some physical limitations, as there is with any vision system. However, with the robustness of the data that this technology creates, you are able to do a lot of computational analysis in order to help overcome these limitations. And if you'd like more information on this, I would suggest looking at our previous artificial intelligence and machine learning webinar, where they go a lot deeper in terms of the data side of things and what can be done on that front. And thank you very much.
Awesome. Thank you so much, Michael. So we now have an opportunity for Q&A. If anyone has questions they'd like to ask of either Michael or Priya, they're both available to do that. And you're welcome to use the Q&A button down at the bottom of the screen. While we're waiting for questions to come through, Priya or Michael, you're running the running the slides. Can I ask you just to jump down to the reminder slide, which I think might be the next one? So there are a couple things to remind everybody of. First is that we'll be sending out a follow-up survey tomorrow. So we'd really appreciate your feedback and thoughts on how the survey's gone, or how the webinar went, and anything we might be able to do differently. And also to let you know that while we don't have a specific plan today for another webinar, there are more coming. Probably late July or early August, you'll see an announcement come out for another webinar. So we'll look forward to seeing you then. So please make sure you watch your email. You'll get one from either Jen Gingrich or from Kevin Turnbull, our head of sales and our business development person. So we'll give a couple more minutes for questions to come through. Priya, I'm wondering whether maybe you could jump back in for a minute and talk a little bit. You mentioned earlier about how easy it is for us to swap out the lights in the spectrometer in the field because of all the calibration work we do up front. Wondering if you could maybe jump in and give us a little bit more information kind of on how that process works and how we make sure that everything stays standard and that it is really easy, because it looks like when you watch the video and you watch the level of work that you do, there's an awful lot that goes into making sure the lights in the spectrometer are set up right. And I think it might be helpful for everyone to understand how we make sure that we stay consistent and how easy it is to swap out in the plant.
Sure, Heather, that's a very good question, because right when we talk about a spectrometer, it has so many building blocks. We are talking about the camera that goes into a spectrometer, then there is a spectral range that we have to fit, and then there's a point of where you take an image and then you look at the spectral range, and then you have the lights, then you have the lights and the spectrometer assembled together in a system. So what you'd have noticed in the video that after each and every specific component is brought into the picture, each of them have their own calibration. For example, camera runs through its own calibration. We have its initial test. We also run a linearity on that, and it is mapped all to a requirement. So every camera is tested for the same requirement. And once we build a spectrometer, we see to it that the spectral range is consistent across all the spectrometers that we build. So if it's going to see between 960 and let's say to 1600 nanometers, every single spectrometer is going to see within that range. And when we correct it for, when we corrected, for example, we talked about SMILE, they all run through the same algorithm. So the correction is the same when we apply it back to a spectrometer. And the lights that you see there are built to a specific requirement. So every lamps in itself are put on a testing jig, and we run it, and the alignment on the bulbs is done, and it is again mapped on to a specific requirement. And once it comes back onto a smart imaging system, which is held onto the frame, again, it's again tested finally for requirements on field of view, spectral and spatial resolution, the amount of light that the amount of light falling onto the object under test. So everything is calibrated to a specific requirement. And this is important because as we go through initial stages, we have gone back and figured out what the problems are and what are the aberrations that come through the system and how it has to be corrected. So that once the problems have been identified, all of them are fixed with the same requirement, and hence the final build can all be traced back to a requirement. And this would ensure that if there is a light that needs to be swapped, we can build it on our test check and we can swap it right back. And we can be certain that once everything is on, we can go back to the system as it was before.
Awesome.
Hope that helped clear the question.
That's awesome, Priya. Thank you. And Michael, just a follow-on question for you. I know you've been in the food plant and done this yourself, but once Priya's done all her work and we've sent if we had to swap out a light or had to swap out a spectrometer, how long does that usually take on the system?
So thankfully, we haven't had to do any replacements on spectrometers yet, but the initial install of the detector modules is a fairly painless, lift it in, secure it with a few fasteners, and then make sure that do the optics test to make sure that everything is working properly and talking to each other nicely. The lamps, those are straightforward, where it's literally for each lamp, you just remove 2 bolts, and then that's the only tool you need, and then they lift out of the cradles quite straightforward.
Awesome. So it's just a very short process. Awesome. We have received a question from one of our audience members. So can you use this technology in finished packaged good products, such as a bag of microwave popping corn?
I'd say that's one of those situations where it's sort of the cop-out answer of it depends. As mentioned before, there are some materials that this technology will just be able to see through, as it is transparent within the wavelengths. Specific plastics and thin materials. So it all depend on what the packaging is made of and how much it absorbs. If it's too thick or there's too much absorption, you'll be losing all that information by the time it reaches the product, and you'd just be seeing the reflectance of the packaging.
Awesome. Thanks, Michael. That's great. So it looks like we've answered all the questions that have come through, and I know we're getting close to time. So I think we'll say thank you so much. Please don't forget to fill out the survey, and please do keep an eye. Oh, you know what? I see one more question coming through. So give me 1 second here. Let me see if I can open it up. I have too many windows open here. Once the system is installed in the plant, how often do we have to modify the presentation of the product into the machine? And in this case, the example is ground pork.
So this would be one of those things where it would just be only once, and then hopefully it's set it and forget it. So what we've done in the past is we've worked very closely with our customers to try to replicate how the product appears in their plant at our own facility, so that way we can do all of that characterizing in terms of what the performance will be in-house before it even goes out. So in a sense, it's just a question of setting it up and then verifying that it works. And then over time as well, as you get more data, the machine learning algorithms become smarter and smarter. So that way, if stuff does begin to change, it'll know more. So like, this is what pork looks like, and anything else shouldn't be there, sort of thing. So yeah, it's one of those things where it's just set it up once, and then as long as nothing changes too extreme, like if all of a sudden you go from very like a very fine grind, very close to the belt surface, to like trim where you're a few inches off, then some changes in terms of the optical system will need to be considered to sort of compensate for that very large change in height.
Awesome. Thank you so much, Michael. And thank you so much to all of you for joining us today. We'll look forward to seeing you a little bit later in the summer on our next webinar, and I hope you all have a terrific afternoon. Thanks again. Bye for now.